So with the cold water, it's spread out pretty quick all around the bottom. And the warm water, it's really taking its time to spread out. It really hasn't reached the bottom yet. I see kind of a big swirl of dye in the warm water. There's a really thin swirl of dye in the cold water. It's been about a minute since I put the food coloring in. The food coloring has taken over the entire glass of the warm water, and there's still some the top of the glass, it kind of all sunk in the cold water. Here's part 2 of the experiment. So this is the cold sample, and this is the hot sample. We'll go ahead and place a timer for 10 minutes and put this one in the freezer. Okay, so it's been about 10 minutes with both the sample in the freezer and the sample in the hot water. Let's see what happens. So right away it just started to fizz, and now it's bubbling around the rim of the bowl. When I added the baking soda to the cold sample of vinegar, it rose pretty quickly, but it really just got fizzy. I'm really not seeing that many bubbles form. The reaction in the cold was definitely more violent than the hot sample. It's been about 5 minutes since I put the baking soda into the bowls, and you can see right away that the warmer sample is still bubbling while the colder sample stopped. So this is an example of how the molecules are still colliding in the warmer sample but have stopped. And that increase of kinetic energy increases the collision of the molecules. I feel like this has an impact in real life due to cooking when you're boiling water. So in warmer water, when you're cooking with warmer water as heat, the collisions can transfer from the food to the water, as well as when you're cooking in warmer water, the collisions can also happen within the food itself, between the pieces of food. So overall, in both the food coloring experiment and the vinegar experiment, it can be shown that the molecules collide quicker in the warm water because the temperature of the water increases the kinetic energy.